To start with, the first SOLARX webinar is titled Modeling of Complex Energy Systems in energyPRO, and we will explain the SOLARX case. Some housekeeping. This event is being recorded already, and some highlights will be shared on the SOLARX website. For you to know, you will have here a chat box below, so in case you have any technical issue, you can write here and we will try to fix it as soon as possible. And if you have scientific questions, you have as well the Q&A box. So in the end, we have a panel discussion, so you can start sharing already, and then we will try to discuss in the end. Professor Jérôme Barrault from University of Lleida, the coordinator of SOLARX, will present an introduction of the project, and then Marta Murkowska from EMD International will follow with the approach of the modeling in SOLARX by energyPRO, and Anders will follow as well, sharing some results with the modeling. In the end, as we said, we'll have this panel discussion. All of you are welcome to interact. I will stop sharing so that, Jérôme, you can share your own screen.
So, good morning. Thanks for participating. So, as Miriam said, I'm Jérôme Barrault from the University of Lleida in Spain, and I will try to give an overview of our project, SOLARX, that is called a dispatchable concentrated solar 2X energy solution for high penetration of renewable energy. So it's a Horizon Europe project in research and innovation action from the call of next generation of renewable energy technologies. It's a 3 years project. We have passed half of it right now, and with a funding of 3 million euros. Just let's have a look of the consortium. So we are University of Lleida in Spain, HyGear in Netherlands, focused on the hydrogen management handling. Acciona from Spain, focused mainly on carbon capture strategies and also the definition of the CST receiver. I will give more information of each of the components later. EMD International, so focused mainly on the simulations of this complex energy system. So with, for example, Marta and Anders here. Fraunhofer ISE from Germany, focused on the solar management. The DTU, Technical University of Denmark, focused mainly on also other types of simulations, but also life cycle assessment and other stuff. CNRS is focused mainly on the production of high efficiency CPV cells and also on the hydrogen receiver, high efficiency hydrogen receiver. And finally, Accelerment with Miriam here, focused on the management of the project. So just to explain the motivations, the context, basically, we know that the share of renewable energies is increasing along the years. So in the last years, but also in the scenario for both 2030 or including 2050, if you want to reach net zero emissions in 2050, of course, we need to increase the part of renewables. How, as we can see in all these graphs from the International Energy Agency. But mainly these renewable energies are intermittent renewable energy systems. So you get energy with PV when there's sun, and we get energy with wind power only when at the moment we have wind. So it's very intermittent and it's not dispatchable. So if you go, for example, from the models we have, roughly we can describe it as we have a base load produced by nuclear energy, but also renewable and intermittent energies, and we fill the gap between this production, this generation, and the demands through systems that are that relies basically on fossil fuels. If we want to reach net zero emissions in 2050, we need a fully renewable energy system, energy mix. And so we'll still have, of course, renewables, variable, intermittent renewable energy systems like PV and wind. But we need to fill the gap between this production and demand through dispatchable renewable energy systems. And this is the main motivation of the SOLARX concept. So just to try to explain it briefly, the SOLARX concept relies on solar field and heliostat field. So there is of mirror that focuses the sunlight onto the top of the central tower. So like in conventional CSP plants, in which normally you have one receiver that is a thermal receiver that produces heat, and after that you just turbine it in a power block. In this case, we have 3 receivers on the top of the tower. We have a high efficiency CPV receiver to produce electricity, a high efficiency hydrogen receiver to produce hydrogen, and a CST receiver. In this case, we don't have further development. It's a quite developed technologies yet. So we just use the data from Acciona that is a relevant factor in this field. So once we have these 3 energy vectors, we can handle them in different ways. We can store them or feed them directly into the grid. If we store them, after that we can use them to produce different kind of products. For example, for electricity, it can be for industry, for residential, commercial, or for producing ancillary services. We will see how right now. With hydrogen, the sectors are transport, or producing syngas for industry and synthetic fuels, but also for metallurgic industries or other ones. And for the heat, so we just can use it for industry in solar heat for industrial processes, use it as in a conventional CSP plant, or also using it to feed into a district heating and cooling network. So here we have 2 of our key technological elements that are the efficiency PV receiver. We'll explain it more in depth in the next slide, and the hydrogen receiver. So here, as you may understand, the basic, the dispatchability and flexibility is obtained through the smart management of the heliostat fields. That is, at each moment we have to decide on which receiver or receivers will focus the sunlight in order to produce one energy vector or several energy vectors at the same time. How do we, which is the criteria for this kind of decision? So it will depend on the application. If we want to just feed electricity into the grid, so we can focus the sunlight onto the CPV receiver to produce electricity at high efficiency. But for example, if the demand is low at this moment, or the price is low at this moment, we can just focus on the hydrogen or CST receiver in order to store these energy vectors, and after that, using a fuel cell or power block, produce electricity at a time in which the price is higher. So this gives us this flexibility. And also, for example, for an industry application, in this case, what we want is just match the production of each of the energy vectors to the demands of these energy vectors inside the own industry. So here, of course, there's a lot of data to take into account. The basic one, of course, the solar forecast. It's our solar resource. The storage levels to decide if we can store more or if we have to produce directly. And that is relevant, the real-time energy demands for industry or energy prices when we want to feed into the grid. So all this system must be studied in a techno-economic way, and we'll see how we plan. We are right now doing it through EnergyPRO, and also environmental and social assessment is included in the project. It's a low-tier project, but of course we need to generate the inputs for future implementations of the system. So a few words about each of the key technological elements. So the smart resource management, this is the one that is able to provide the dispatchability, that is able to provide ancillary service to the grid operators, and it's based on artificial intelligence strategies, and we'll assess the impact of these strategies, of different strategies we have developed through EnergyPRO. The CPV dense array receiver is another key technological element. In this case, SOLARX plan to develop a CPV cell with a high efficiency of 45.9%, and also we want to bridge the gap between the CPV cell efficiency and the receiver efficiency, the CPV receiver efficiency. This gap is quite high normally, so we want to address each source of losses at the receiver level, like mismatch losses and pumping power for the pooling function. Our objective is increasing the efficiency of the receiver by 30% with respect to the current state of the art. And finally, a B-energy hydrogen receiver that can work both with solar energy or electricity, for example, in periods in which we have curtailment, so we can use electricity surplus from the grid to produce hydrogen using natural gas, but also biogas, and as we also incorporate carbon capture and user storage strategies, we're able to work in a carbon negative way. So all these data, in order to see how do we assess the impact of our solution. So we have the CFP receiver data from Acciona, the three KTs that are developed in parallel: solar management, high CPV efficiency receiver, and B-energy hydrogen receiver. All together are integrated into a technical model that make possible to assess, to validate the SOLARX performance technically. But when we include demand scenarios, system costs, regulatory framework, like market prices for each of the energy vectors, for example, we're able to go one step further and assess the SOLARX economic impact to different KPIs, some recommendations for the sizings of the systems as a function of location, type of applications, etc., and identify the relevant parameters that are an impact on the performance of the system, of the concept. That will help us to define the future strategies, implementation strategies. So just to resume the scenarios, in that we are talking about different kind of applications. It can be a general one to feed electricity into the grid, to feed each of the energy vectors into the grid. Industry, in this case, what we want is to match the energy demand. And islands, this is another use case in which also what we want is to see how SOLARX is able to reduce the CO2 emissions associated to the production in isolated islands, and also the dependency of fossil fuels that is very high at this moment. We'll do it for different locations. From the locations basically defines the price of each of the energy vectors along time, but also the solar resource, solar radiation. We'll have some explanations about how do we do it in order to integrate all this data into the SOLARX model. So different kind of metrics, LCOE, internal rate, and cost of valued energy in order to assess the performance and compare it with different current technologies. All that I will not enter into details, but will allow us to define the expected outcomes and answer to the needs of the destination impacts. So basically, about the challenge, it's just to demonstrate that SOLARX is able to provide dispatchability and flexibility, and at the same time being able to maximize the owner benefits, and so making the solution attractive for investors, grid operators, industries, and citizens. So, and also we want to assess the impact of this kind of solution on the capacity to increase the share of renewable energy solutions. So, to detail somehow have the design and trial of more efficient CPV and B energy hydrogen receivers, so the conversion technologies, provide the smart resource management system, and demonstrate that it's able to align the production with the energy demands, or the production with the hours in which the price of the energy vectors is high, and create a roadmap towards the system integration and technology commercialization, and assess the economic, environmental, and social impact of the SOLARX solution. I think perhaps I've been, no, it's okay for the time. Basically, if you need some more information, so you can ask questions, but also you have here the contacts of myself and Miriam, that is the communication dissemination manager. So thanks for being here.
I think I will now take over, and we will dive into the approach for the modeling. I will share my screen. Hope you can see it now.
Yes.
Perfect. Good. Yes, hello, welcome. I'm very happy to see so many of you interested in the SOLARX project. I am going to follow after Jérôme's introduction to the project with what we at EMD been doing about the approach and how did we model the SOLARX project in energyPRO. And I'm going to start with a slide that also here contains a model of SOLARX. You could see a nice graphic that Jérôme presented. And here we have the first model that we developed of the SOLARX project, where we are talking about a little bit limited part of it. So we are modeling the solar field, and we are modeling the concentrated photovoltaics and the thermal receivers together with a hot molten salt storage and a steam turbine. This being, as Jérôme also mentioned, a more mature technology. And all of these are then connected into the day-ahead market. So in the first analysis, and what I'm going to take you through today, we are leaving out for now the hydrogen receiver. But we built this energyPRO model with all of the technologies and optimized its economics based on the participation on the day-ahead market. Anders will later also show you the model and all the cool things that it can do in the modeling. But so as you could see, this is these are the technologies that we modeled. We based our simulation on Spain, and we are modeling year 2023. For the inputs to the data, as already mentioned, we need the solar resource. So we need an irradiance data set that we can use for our calculations. What we provide at EMD and in energyPRO is the Heliosat SARA-free dataset. That's a dataset that can provide us with direct horizontal irradiance, and it covers, as you can see here on the map, Europe, Africa, and part of Southern America. And this is the source that we are using for the modeling. It's very easy to edit for a specific location. You simply have to select where is it that you would like to download the data for, and then we automatically download the data, and we can use that in the SOLARX model. So since we are provided with direct horizontal irradiance, and in the case of SOLARX and in actually all the concentrated solar applications, we are talking about the normal irradiance that we need to have, since we are tracking the sun position to reflect it to the receivers. What we had to do is also implement a very simple formula for converting the horizontal irradiance into the normal incidence irradiance. And that is done also in our energyPRO model. The other source that we are using in this simulations is the day-ahead prices. So as Jerome mentioned also, we are talking about optimizing the economics of that model, and we are doing that based on the day-ahead prices, the Spanish, in that case, day-ahead prices for 2023. Here you have a long time series, the full year of prices. You can see quite high fluctuations. If we zoom in into the specific, I think here we are having a week of data. You can see something that is quite common in Spanish conditions, and actually not only Spanish nowadays, but since they have a high penetration of solar, you can see that we have a very low prices during the peak solar productions. So here around noon, we are getting way lower prices than the other hours of the day. That is also something that the SOLARX technology is focusing on. So we can actually dispatch the energy in the hours with higher prices. Hours with higher prices also being the prices where the energy is more needed. So this is what we are also aiming for, and I believe Anders will also talk about. Another input, and that's maybe a lot of numbers here, but as I said, we are modeling the solar field. We have input from the Fraunhofer-ISE analysis, where they provided us with the specific flags for the CST technology, so the concentrated solar thermal. This is the specific flags that will hit the surface of the CST receiver depending on the sun position. Here we have the azimuth of the sun, so where is it? We can basically say for each sun position that we have, for each of these azimuths and these altitudes, what is the specific solar flags we can expect at the receiver, assuming that we have a perfect DNI, so 1000 watts per square meter DNI. And between all of those values, we are simply interpolating and finding the flags for all the sun positions. The same goes for CPV, so very similar input we got also from Fraunhofer about the CPV. You might notice, although there's a lot of numbers, but we can also look here, that the specific flags, there is a difference between the specific flags available for the CST and the specific flags available for the CPV. The one for CPV is a little bit lower, and this is caused by simply the solar field way of reflecting it to the receivers. In our analysis, the CPV receiver is put higher up on the tower, meaning that we are less efficient in aiming at that point than it is for the CST. And also there is a difference in the area. CST is bigger, hence it's easier to aim at that receiver than it is for the CPV. So you can see here that for the same sun positions, we actually have a specific flags for the CPV, which is a little bit lower. I am also bringing it up here because I am gonna show you the next slide, in which we are talking about how we modeled the solar field, and Anders will also show you that in his part of presentation. But what we are doing here is that we are having the solar field with all of these information about how much specific flux we can get. The input to that solar field is the DNI, so we can we of course account for the real DNI conditions. And what we are producing here is the solar flux for the CPV. And here, to be able to model it in energyPRO, we added a unit allowing us to convert the CPV flux to the thermal flux and then use that thermal flux in the CST. That is done to account for this difference between the available flux from CPV and CST. This graph here is something that we can also produce in energyPRO, that is showing us what is the specific flux in each hour of the day, so the maximum available specific flux from the solar field for each hour of the day. And this we are basically this information we are actually using in the solar field. So all of the data that I showed in the previous slides, we are transferring it into finding what in each hour, what is the specific maximum flux, and then using that together with the DNI data to simulate. And the next technology is the concentrated photovoltaic CPV. And this is something that the Yale University is working on. And we got the information about the efficiencies we should model from them. We modeled it simply as unit that is needing an incidence power on the surface and producing electricity. And how we modeled it, you can see it here. So we have a dependency between the incidence power and the output power of the CPV. And that dependency, of course, the higher the incidence power, the higher output power we can get. So the output electricity from the CPV. However, as you can also see here, we have, I've plotted here also the efficiency. We had the highest efficiencies at lower incidence powers. It's simply because of the thermal behavior of the CPV. If we have very high incidence power, we also decrease the efficiency slightly. And that is also reflected in the model here in energyPRO. The next part that we have is the CST. So we have the concentrated solar thermal model as well. And in here, it's again a simple model that we got information from Acciona and a publication done by Montes. We have an information about what is the efficiency of that unit depending on the incidence power. Here we have the higher incidence power, the higher the efficiency we have. And this is also, this characteristic is included in the model here in energyPRO. The next component that we are talking about is the molten salt storage. We got the information about the temperature levels and yes, the size, although we are also optimizing the size. So that's here is just to show that there is a possibility to say what is the storage content in both of these tanks in the cubic meters, so we can define, of course, they are connected, meaning that we are having the same storage content for hot and cold molten salt. But you can define that in the program. And here in the model, we specify the parameters so that the molten salt cold storage tank has 290 degrees and the hot storage tank has 565 degrees Celsius. And this is used also, so the hot molten salt is heated up by the CST. Then in that case, if we are using the CST, we are taking the cold molten salt, heating it up in the CST and putting it into the hot molten salt storage tank. And then when the energy is needed, and that is also something that we'll show later, but this allows us to actually produce the electricity in the steam turbine in the hours that we makes most sense for us economically. So we can take then the hot molten salt and cool it down in the production of steam for the steam turbine. Yes. The last part of the model, or actually the second to last, if we also consider the market, here we have the steam turbine, and we have quite basic assumptions here, saying that we have the steam generator efficiency of 80% and the power block efficiency of 39%, giving us a total efficiency of 29%. And that is the efficiency that in the transformation of the energy from the hot molten salt to electricity. And here also we have the day-ahead market. That is something that I already briefly mentioned. We modeled it with the Spanish 2023 prices, and we have the full hourly values. And all of this analysis is also done on the hourly time step. I think I am not sure if I'm running out of time, perhaps. But I now actually am going into a little bit into Anders' part as well. We agreed that I'm also gonna have a short introduction for the part of the simulations that Anders will show you in a moment, and for the results of the SOLARX project modeling in energyPRO. And here, just to give you an overview, we did perform a sizing exercise. So how big should the different units be for the system to operate best and provide us with the best economics. And we have the assumptions about the cost here. These are the costs we use for all the different components. I will not go into many details here, but this is what you can also go back and see here. With these costs, and we also introduced something that is nowadays talked about a lot. It's that we are no longer have to look only at LCOE actually, but we should also be looking at the cost of the value of the energy on the market, because we can minimize the LCOE, but that doesn't really give us the same as talking, okay, when is it that my energy is actually needed in the system? It's becoming more and more of a challenge, and that's also something that Jerome mentioned. So for that, we used in our analysis the cost of valued energy. It's the concept that actually DTU first introduced. And in here, I will not go much into these details, but in here what matters is the hourly price and the hourly production as well. So we are not only talking about the production of energy divided, so the cost divided by the production, but it also takes into account the prices and the variations in the prices over the day. And with this, we did the exercise of sizing our system, and what we arrived to is these results, where we can see that we have the lowest LCOE for a smaller size of the hot molten salt storage, and that gives us the lowest LCOE. However, for the lowest cost of valued energy, we actually are talking about a higher size of the storage, and that is also something I believe Anders will touch upon, but that's also showing the value of flexibility of the SOLARX system. And that was all from me. I think now Anders will take over. I will stop sharing.
Yeah. Thanks for your interest of looking into this model. Martha has shown this overview of values calculated by this model. I will later on also show you a more complex model where we also produce hydrogen, but we'll start with this one. The bottom line, here it's only optimized to 1 month, but it is this bottom line that will be optimized when using here the MILT solver. You can choose between 2 open source solvers and a commercial solver, or use in some examples our own optimizing tool. Making production graphic shows here the upper graph I have chosen to show the direct normal irradiation. Then day ahead prices in Spain, very low prices here, Sunday to the 3rd of September. The electricity production on the PV here, Friday the 1st of September, and here the electricity production on the steam turbine, the green one. In between, before this production on the steam turbine starts, we'll fill up this 800 cubic meter molten salt hot tank. When starting the steam turbine, it'll empty. And you can see the operation income both here but also down in the report. But here is something strange going on, that the steam turbine runs in only 1 hour and only part load, and that could normally be not acceptable. So what we are doing when we begin to optimize the operation is also to take care of such operations. Even if this solver, the MILP solver, mixed integer linear program solver, finds this as an optimal, then we will say we don't want that. We will only full load the steam turbine, and every new constraint that comes up will reduce the operational income. I will remove that it is allowed to, and now it has removed this one, but it will re-evaluate all hours in. Here it's only 1 month, but normally you calculate a full year. But put in a full load hour here, and one could say, that is only using 1 hour. Yeah, but then you would begin to say, aren't there start costs on such a turbine? So I will add a start cost on the steam turbine. This payment concerns a production unit, and here the steam turbine, and it is turn-ons. And what about saying that such a 12 megawatt steam turbine at least costs 100 euro for a start? So now there has to come up one extra payment in the operation income, and still now the MILP solver shall take into the account that this extra cost shall also go into an optimization. And now it begins to look much, now it has removed this 1 hour production here and moved it to the day before and day after. We can see the content in the hot molten salt tank. And as I've said before, then when we begin to produce electricity on the steam turbine, it will move cubic meters from the hot molten salt tank to the cold molten salt tank. I could also show you the cold molten salt tanks. Yeah, but Another thing that Marta showed you was that we have tried in energyPRO a lot of different capacities. We could, for example, choose to have a bigger tanks. Instead of 800 cubic meter, we could. Here it has been made by formula, because you start with time series and time series function. But if we say we double the hot molten salt tank and also the cold, it will improve the operation income. It now is 1600 cubic meter in the hot molten salt tank, and the operation income that now also include the start cost on the turbine, 46 times that month of the 100 euro per start is included. Yeah, I'll just show you another model we have worked with in SOLARX. Here it becomes a little more complicated, that we have a biogas plant delivering biomethane that can be stored in biogas storage. We can either sell the biogas, or we could take the biomethane and produce hydrogen. We can still use the concentrated solar power to either produce electricity or run this hydrogen production, or covering. Here I have put in a steam demand, where a boiler will take the steam demand if it is not delivered by the SOLARX plant here. A lot more complicated optimization. Yes. I think I have run out of time. So just to say that in SOLARX we will work with these multi-vectors and model them in energyPRO. Thank you.
Before, just to say my apologies. When I explained the consortium, I forgot to update the slide from this is our previous slide. Now we have another partner into the consortium that jumped in the last month. That is the Cyprus Institute, and so that is here basically to help to characterize the solar field and ensure that the solar management strategies work well. So just to update with that, and so I will switch to the question from Alaric Montenon. Which nominal power of the CPV, which is the nominal power of the CPV? So it's we are working on a design of the facility that is a modular design. That is, we have several solar fields associated into a single central tower. This is a tendency that appeared in CSP, but also in the only CPV experience that exists in the world in Australia, in order to reduce the cost and doing it more modular and being able to cover different ranges of powers. Yeah, the people is going on that direction, and we also believe from the first simulation that this is the right one. So relatively small field areas for each tower. In this case, each module of that is I'm talking about central to more each associated solar field. Each module consists of one PV nominal power in each tower is 1 megawatt electrical megawatt. Okay, so around 2 by 2 square meters. And there's also part of the question is, does it require active cooling? Yes, of course. Here we are talking, we want to reach 1,000 strength of solar concentration in order to also to reduce the cost. So of course, yes, there is the requirement of active cooling, and this is one of the parts that we are working on in order to reduce the mismatch losses, okay, by trying to make more uniform the temperature of the CPV receiver, and so avoid this mismatch, and also at the same time lowering the pumping power needed. Okay, so through dedicated design. I hope I answer your question. If not for everybody also, I think that you can send your question. You have our website to get more information, and also there you can find our contacts, but also you can ask us directly by mail if you want.
Could I have these? If there's no other questions, I could have the last 5 minutes.
If there's no question for the people,
this was the little more complex model. If I close that one, that is when you open energyPRO, you will meet energyPRO this way, and then it is really about throwing a lot of components into energyPRO. For example, I had a demand of 2 megawatts constantly in all hours of the year, and now I have a boiler of 4 megawatts, and then it would be nice if it could do it. So the mill solver says there is no solution. Then I could ask, allow it to partial load. Now there's a solution. But it is really about making such a complex SOLARX plant. Throw all the components into this GUI and connect them and define the constraints of operation, add the payments, and then ask the mill to optimize in which hours shall each unit operate. That was a quick EnergyPRO course, wasn't it?
Thanks, Anders. So now 2 questions for you, Anders, or Marta, if you want. The first one from Eric Montenon. Is there already a built-in library in the software? Also TMI files, especially for the components of the project that you presented?
That is a part of the SOLARX project that eventually we will, when we have validated these components, they will be accessible in EnergyPRO.
Okay.
And we do not have TMYs, but we have data for specific years. So we do not work with typical meteorological years, but we do have specific years data.
And also, thanks both. Another question from Ismail Logmari. Is there any consideration for the uncertainties, whether for prices or DNI forecasting performance?
So currently we didn't do that sensitivity analysis, but we are talking about, I mean, we haven't discussed irradiance yet, but we could of course do that. And but we are also talking about making these analysis with prices from DTU's forecast. They have the forecast for the future price scenarios. So this first sizing exercise we did with the 2023 prices, but of course it's difficult to say what the future prices will look like. We will have some insight to it thanks to the DTU's models, and we will use that in the analysis. But yeah, it's a very good point.
Danish Energy Agency gives these hourly values for future years, where they have modeled when we develop wind and PV, and how will these hourly prices changes, so that we will get a more steep duration curve, but still it is as hourly values that can be imported to energyPRO to test.
Indeed, maybe for the next SOLARX webinar we can take DTU and discuss kind of a forecast and an outlook of the upcoming solar forecasting stuff. So I think it's a really nice question to close the webinar. Maybe Jerome, you would like to say something else? Otherwise, we are just on time.
No, just thanks for participating, for your interest, and happy to answer any other question you have.